Hello, welcome to this talk. I'm the speaker liaison. During this talk, please submit your questions to Swapcard. You can, if you don't know already, you can do that by going into this event in Swapcard, and there's a big button called Live Interactions, and there you can write your own questions, and you can also upvote other people's questions. So please do that, and if there's no time at the end of this talk, we'll take those questions in the office hour. So please join me in welcoming Einar Urdshals, an AI safety researcher at Timaeus. Timaeus is a research organization focused on ensuring the safe and beneficial development of artificial intelligence through a better understanding of deep learning. Einar holds a PhD in physics from Chalmers University of Technology, where he explored the intersection of particle physics and machine learning, and now works as a research scientist applying singular learning theory to transformers. Please give him a warm welcome.
Okay, so why are we here? Well, we're here because AGI is coming. So in this chart here, you can see various kinds of tasks, and the bar there of 0 is human performance on the task, and the curves is the performance of AI relative to humans. So you can see on more and more tasks, the AIs overtake humans. There are, of course, still important tasks like complex reasoning, where the AI is quite far off, but it's getting there. You can also look at the evaluations by meter, where they rank the difficulty of a task by the amount of time it takes a human expert to complete that task. So that's on the y-axis here. And then you can plot the performance or the difficulty of a task that an AI can solve on the x-axis. And in log, you can see that this is roughly aligned, and with a doubling time of every 7 months. And like it actually might be quite a bit worse than that, because if you only look at the last models here, which are the reasoning models, they are quite a bit steeper, with a even shorter doubling time. So AI might be coming rather soon. If you want to read more about that, you can check out this meter report. Now, of course, there is some caution that is warranted. So there is a strong incentive for various actors to exaggerate the speed of AI progress. I mean, there's a lot of money to be made from claiming that AI goes faster than it does. Also, some of these benchmarks that takes a human an hour might actually be easier than you think. And like, if you know the whole internet, then kind of maybe this is actually pretty easy. So if you want to read more about like why it might be that AI is further away than you think, you can read this short form by John Wentworth. So AGI is probably coming, maybe sooner, maybe a bit later. But what could go wrong? Now, of course, one obvious thing that could go wrong is like various forms of misuse. So AI will probably make it easier to make various kinds of weapons of mass destruction. It will make hacking and cyber offense easier and more accessible to a lot of people. And I mean, one are already working on various forms of autonomous weapon systems that are being used today. And these will probably get better and better and more scary. Also, like, if we get another entity that is smarter than us and better than us at like a lot of things, we might just become less and less important and less relevant. And we might just end up in a situation where humans are no longer needed. Or the AI might do some kind of treacherous turn, sudden takeover, where it does things more or less on its own, and it kind of figures that it would be better if it was in charge rather than us. This is something of what's happening in the AI 2027 forecasting, which you can read here. So what's the current plan to deal with this? Well, the current plan is to do various forms of safety training and evaluation, such as reinforcement learning from human feedback, and then to do these AIs that you have, and then to use AIs that you have been safety training to help you monitor other AIs. And then you hope that you notice if your safety training fails, and that in general, these safety training goes well, and that you live happy ever after. Now, of course, that might not happen because safety training might be rather shallow, as is illustrated by the Shaghat meme. It might be that the AI sandboxes and tricks the evaluations by underplaying its capability if it understands that it is being evaluated. This is happening already. And of course, the AI that is tasked to monitor other AIs might either be tricked or might collude with the strong AI that it should task. Basically, the superhuman AI might be better at sweet-talking Claude than you are. And then it might get Claude over to its side, even though you have done a pretty good job at aligning Claude. So in order to make this not happen, we need a better understanding of what the AI learns and why. And we need a more robust understanding of the theory of deep learning. So that's where learning theory comes in. Now, classical learning theory paints a picture where you, as you make your model bigger, you go from underfitting to having a good fit with the right size of your model to overfitting. And like classically, it looks something like this. So like as you make your model bigger, your training error goes down, but your validation error goes up. But now this is not actually what we see in deep learning. So the size here varies on the x-axis, and you can see that like as long as your model is sufficiently small, the result from classical learning theory holds. So you get that as you make your model bigger, initially it gets better, and then it gets worse, but then it gets better again. And when it gets better again, it gets even better than it was at the beginning there. Another thing which you also wouldn't expect from classical learning theory is the phenomena of grokking, where if you train on some data, then initially you get, on some tasks, you can initially get 100% performance on the training data, but really bad performance on the test data. But then eventually, if you just keep on training, you hit something that eventually generalizes. So even though whatever the model has seen does just as well, so the model does just as well on the training data that is seen here as it does here, but still, if you train for long enough, it ends up here in the solution where it has generalized. So there is some kind of inherent bias towards generalizing solutions. So why does classical learning theory fail? Well, it fails because it assumes that all the parameters in your model do something. I will come back to what that means in a bit. Now, if you relax this assumption and you assume that you can have useless parameters in your models, then you get a bunch of problems with the maths. Now, this has been worked out in this book from 2009. And with that, you get what's called singular learning theory. Now, what does it mean that a parameter doesn't do anything? Well, so we call a parameter. So we call a model singular if it has parameters that don't do anything. And by that, we mean that there are combinations of parameters that can be changed without changing the loss. So you see, if your loss landscape looks like this, so if the loss here is on the z-axis, you can see that there are parameters here that you can vary. You can walk around in this loss landscape without increasing the loss. Whereas if your loss landscape looks like this, no matter how you change your model, your loss increases. And what's very important is that for singular models like this, the generalization error does not necessarily go up with the number of parameters. Okay, so to then quantify how singular a model is, we quantify that using what's called the learning coefficient. This will be the most technical slide. So like, if you kind of like zone out when you see maths, this will be the most technical it gets in this talk. So, this slide is the most technical. So the learning coefficient captures the volume scaling of the local basin in your loss landscape. So you can show that like if you're very close to the minimum, then if you have some tolerance in loss epsilon, then the volume of parameters in which you have a loss smaller than your tolerance scales like a constant times your loss tolerance to the power of this learning coefficient. Okay, and now why do I care about the learning coefficient? Well, you should care about the learning coefficient because that matters for which model you end up with in the end when you train. Because you can cast model selection as a form of free energy minimization in physics, where you can show that the free energy formula that the model wants to minimize is this combination of the loss and the learning coefficient, which captures your complexity. It is something like how in physics often have some trade-off between the energy and the entropy of the system. And this trade-off depends on the size of your data set. Yeah. Okay, now mostly all the technical stuff is over. So yeah, okay, cool. So now this matters. This is less technical, okay? It's not just equations, it's like drawings and stuff. It's like, okay, cool. So this matters because if you then have multiple minima, then depending on how much data the model has seen, you will either prefer a broader minima with a worse loss, as you see here, or you will prefer a narrower minima with a better loss, as here. And there is some critical amount of data where there is a kind of phase transition between one solution and the other. And to say it like simple words, it's like you can end up with a problem where you over generalize. So you kind of perfectly specify the kind of solution that you want, but still that's not what you get, because there exists some other solution that is sufficiently close to the thing you wanted and a lot simpler, and therefore the model ends up learning that, even though you did a really, really good job with specifying the loss function. So to kind of apply this to AI safety, take the case of the paperclip maximizer. So the paperclip maximizer is a classic example of AI misalignment, where one trains an AI to make paperclips. And you want this AI to be efficient at making paperclips, so you train it to maximize the number of paperclips it makes. Of course, when you train an AI to maximize the number of paperclips, what you mean is maximize the number of paperclips within kind of reasonable bounds, right? Don't seize the means of production. Don't like take over the earth. Don't like kill humans. Like just make as many paperclips as you can within whatever reasonable bounds that all humans understand. Now, the problem is that like reasonable bounds that all humans understand, that's pretty complicated. Now, a much easier thing or a much simpler thing is just literally maximize the number of paperclips. And in the paperclip maximizer scenario, that's what the AI ends up doing. And it ends up seizing power and turning the entire Earth into paperclips. So if one then has an understanding of the learning process, one can understand how much data do you need, of which kind, in order to have the more complex solution be preferred over the simpler solution, which you don't want. So I will leave it there, and I'll have time for some questions. So in summary, to ensure that AGI goes well, we need to understand and control what the AGI learns. And understanding this kind of learning dynamics using singular learning theory seems like a promising way. So basically, the cauldron of AGI is cooking. Let's make AI less like alchemy and more like chemical engineering, where you target and you get the thing you actually want. You don't just pour a bunch of things into the cauldron and stare, and you get something out that you don't know what is. Thanks.
All right, we have some time for questions. Now you can still submit questions on the swap card, so please do that now. And we'll start with one. So what are the assumptions of the free energy formula or ideal Bayesian learning?
Right. So the assumptions are just that the model is doing Bayesian updating, which is that it's in an optimal way extracting information from the data so that it extracts all the possible information from the data. I don't think there's any other, there's no other assumption that underlies this, just that it's that is doing optimal Bayesian learning. Yeah.
Nice. Next question is, how can the model keep learning when there's already 100% on training data?
Right.
Shouldn't all gradients be 0?
Yeah. So in practice, gradients, right. So if all gradients are literally 0, then the model will stop learning. So in these cases of grokking, there is still some random walk going on, for instance, driven by batch noise. So you can think of this as something like the AI starts in a fairly narrow trench, or so it starts somewhere random, then it trains, and it ends up in some fairly random trench, and then it does kind of random walking around in this trench until it falls into a hole. And once you've fallen into a hole, then if you keep doing random walking there, you will just keep hitting walls, and basically hitting a trench in many dimensions is just really hard. So kind of if you just keep doing random walking in the lost landscape, you can think of this as that you then end up in the broader minimum. So yeah, so this comes from random walking, I think. Although I think this, so that is one explanation, although I think grokking is still somewhat of an open field of research. So I think the last word is not said. It's not fully understand why you end up where you end up. I should stress. Yeah.
So SLT wants to quantify the amount and type of training data to use, right?
Yeah.
Can it also be used to predict the optimal amount, etc., of other stuff?
Yes, correct. So that's the hope, right? So kind of we can then say things like if you want to set your goal to a certain complexity, then the training data that you use to train these values of this goal needs to be of this amount. And imagine that you know that like there are certain things that the models might learn. So like say there's one thing you don't want, which is very complex, but probably has a very good loss. And there's maybe some intermediate thing that you actually want that is fairly complex. And then there's something you don't want that is very simple. Then by tailoring the amount of training data, the idea is that you can then hit the kind of solution you want. If you have an idea of the complexity of the solution you want. So you don't have to literally know the solution and be able to specify it. You just need to have a sense of how complex it is. And of course, you can also then measure the broadness of the minimum you have ended up in and tell, have I landed in a complex or a simple solution?